In this video, we will look at finding the arc length of a curve using parametric coordinates as opposed to rectangular. And I know it's been a week or two since we covered the formula in class, but if you remember, the arc length formula for a curve in rectangular coordinates or as a function was the integral of 1 plus the derivative squared with respect to x integrated, across whatever x values you want. So you can't see what I'm writing. And the reason for that we talked about, but it was due to how we add up a differential arc length, kind of if we're imagining a portion of the curve and we're looking at kind of adding up the curve in individual pieces, we could consider, what is the arc length of each little individual chunk as a combination of delta y squared, by Pythagorean theorem, because delta x squared plus delta y squared would give us delta L squared, or the length of that particular line segment. And it turned out that by the mean value theorem of integrals, we could always there's going to be some position on the curve where the derivative is equal to the derivative is the slope of the tangent line would be equal to the ratio, and we made a particular substitution for this. But if we look at it in a parametric sense, actually, there's an even simpler explanation, and it's a little bit easier to imagine this ratio in a different context. But if we're thinking about the length of a line segment and trying to integrate an infinite number of line segments, and what if we wanted to know what is this dl? And similarly, if we were thinking about this as dx and dy instead, and dl would just be the name for the differential arc length, which would be a different parameter related back to this. We can kind of see that in the way that, essentially this formula was derived from that idea. But not trying to focus on rectangular coordinates right now. Let's focus on parametric, and then shortly after on polar. But if we think about the expression delta x squared plus delta y squared, notice that the algebraic logic is, well, what if we were to factor out a parameter from this, delta t squared? Notice that this makes sense because what I have is delta x squared over delta t squared, and if the delta t squared were distributed, it would cancel. And similarly, if delta t squared was factored into this, it would also cancel as well. So basically, I'm kind of introducing a factor of delta t squared in order to create a ratio of delta y to t and delta x to t. And then since delta t squared is now a common factor, I could split apart the root and take the square root of delta t squared, which would just leave me with delta t. And essentially, this expression is equal to dl as well. And if we wanted to add up an infinite number of little mini arc length segments, we could integrate this expression with respect to t. So again, the delta t would change to dt. All the deltas change to differentials, and we need to integrate to form a series of infinite sum of little mini arc length pieces to calculate the precise area under the curve. Anyways, it kind of fits in line with the idea of, well, what is, if I'm thinking about it like this, dx squared plus dy squared, and I wanted to integrate that sort of expression, which would, essentially give me a differential arc length. Well, the tactic, it's different, where I could just sort of normalize each of these by dt squared, and that would just introduce a factor of dt on the outside. So it's a much simpler formula at the end of the day. Anyways, let's go ahead and try it. Or another way of saying this is, well, we have f prime squared plus g prime squared, because again, we usually represent a polar parametric equation as x is f, y is g. So you could also write this, if you, instead of Leibniz notation, using function notation, f prime squared t plus g prime t squared with respect to t. And if we integrate that across, again, whatever parametric boundaries or limits that I want, whatever t I want, would give us the arc length of that curve in that form. So let's start with the cycloid, because the cycloid, an example we looked at about a week ago in class, which has the corresponding to a circle of radius r, has the parametric equation x equal a theta minus sine theta and a1 minus cosine theta. And so, in this example, we looked at, for the cycloid, what was its slope? I don't believe we calculated the area under it. I could be wrong. I think actually doing the area is kind of difficult, not impossible. But there's something interesting when it comes to integrating with parametric sense. And this is also a notably important historical problem, which we'll talk about once we finish looking at it. Because, for right now, I don't know, it's unlikely that you've heard of the length of this curve, and exactly what this is. But in terms of historically the development of calculus at the time, mathematicians had figured out the length of a cycloid, doing it a lot of other ways. They had a lot of geometric proof of it, but it was kind of an interesting example because they wanted to see, well, if I use calculus, do I get the same answer as I should? Just like, when looking at a circle, it helps us to really confirm that these tactics of integration are doing the thing that I expect them to do. They give me the answer I'm expecting. Not that that's a proof, because obviously the proof of the fundamental theorem of calculus is more important, but it's a good, way of confirming and knowing that if I use these other systems, that I'm still getting an answer that I expect. Anyways, let's throw it in. So, what we need to do is first know, well, what is dx dt, or dx d theta in this case, because again, it doesn't matter whether you're using t or theta. But a will not be affected by the derivative, and derivative of theta is 1, derivative of sine is cosine theta. So dx dt, or dx d theta would be that. dy d theta would just be, again, a will not affect derivative of 1 is 0, and derivative of cosine is negative sine. Since it's already negative, we would have positive sine as its derivative, and there we go. And essentially, if we square both of those and plug them into a square root, that will give us an arc length of a parametric equation. So if I wanted to know the length of one arch of a cycloid, I would need to integrate across the full boundaries of t, which, remember, 2 pi covers 1 period of the cycloid, obviously because it's corresponding back to trigonometric functions. So we're going to integrate from 0 to 2 pi. Notice that if, a lot of times we're integrating from 0 to 2 pi just because that's often what composes like a circle or a rose or whatever, gives us one arc length of the arch. But anyways, so we would have the square root of f prime squared. So this is our derivative here. So we need to square this. So we'd have a squared 1 minus cosine theta squared. And then we'd have plus g prime squared. And so g prime squared would be a squared sine squared theta. And integrate all of that with respect to our parameter. So I'm just plugging this into the formula. Obviously, I'm changing t to theta because at the end of the day, it doesn't matter if your parametric equation uses theta or t. But this is a different theta from a polar equation, not to be confused, which I know can be confusing. And that's why most people tend to use t instead of theta. But at the end of the day, not a big deal. Okay, so what will happen here is, well, of course, a squared is a common factor, can be factored out. And the square root of a will just leave us with a, and we could even pull that outside of our integral. And what that would leave us with is 1 minus cosine squared plus sine squared. Well, we'd have to FOIL this out. So 1 minus cosine squared would leave us with 1 minus 2 cosine theta plus cosine squared theta. And then we also have plus sine squared theta. And we're integrating with respect to theta. And notice this leaves us with an integral which involves a bunch of trigonometric functions within a square root, and it looks quite horrible to begin with. But what's good to know about this is, well, cosine squared theta plus sine squared theta, that actually just makes 1 by Pythagorean identity. So 1 plus 1 is 2. So what we would end up having here is the square root of 2 minus 2 cosine theta integrated with respect to theta. And let me fix my square root because it's a little bit too long now, but basically just simplifying with trigonometry. And this is an integral that I don't think we have seen yet before, but this one's kind of interesting strategically, because actually what we can use an identity, if I recall correctly, to solve this. And it's actually a different implementation of our power reducing identity. If you remember ways that which we've used power reducing identities before, is we basically we've used these identities to reduce the power of sine squared to make it easier to integrate. But what you might notice is the structure, what I'm left with is 1 minus or 2 minus 2 cosine theta. But what I have is something much like this right here. And if you think about the identity backwards, you could take 1 minus cosine 2 theta, and that would actually be equal to twice the sine square of theta. So let me write that all out. What I have is I could factor out the 2. Technically, I could skip it if I really saw what was happening here. But basically 1 minus, sorry, I was supposed to write it. I was supposed to factor out a 2 there. I said it, but I didn't write it properly. I just closed my formula sheet, but going back to the identity, 1 minus 2, 1 minus cosine theta is equal to sine squared. And basically multiplied by 2. So all of this will just be 2 sine squared. However, also important to note is that when you are applying the power reducing identity, the angle will double. Notice that I don't have a double angle here, so I could do a substitution to change it, but additionally, another way of looking at this as well, this angle would be half of this. So if I'm going to, say this is theta, then this would be theta over 2. So let me just write it out and then let's continue, because I don't want this video to get too long. But obviously I want to try to explain everything I'm doing well. But I'd have the square root of 2, and then 1 minus cosine 2 theta is equal to 2 sine squared theta over 2 with respect to theta. And again, it's just because I'm applying the power reducing identity backwards, which says that, in order to reduce this sine squared into a lower power, I double the angle, and it's 1 minus 1/2 times 1 minus cosine theta. And anyways, you can play around with substitutions, and that this should make sense. Anyways, what you'll notice actually, and the reason why I did that at the end of the day is because it takes this more complicated integral and it turns it into a single sine squared. And since we have a square root, we know the square root of sine squared is just sine. And also, square root of 4 is 2. So at the end of the day, this would leave me with 2a multiplied by sine squared. And the integral of the square root of sine squared is sine theta over 2, integrated from 0 to 2 pi with respect to theta. And now, technically, this is where we have a little bit of a problem, because the integral of the square root of sine squared should be plus or minus sine, because we should have an absolute value on here instead, not because when we're taking the square root of something squared, it's always equal to the absolute value of that. And that does matter in terms of what our answer becomes. And additionally, we could solve this integral by a simple u sub, but let's just use a calculator to do that, because why not? And we'll try to wrap this up. Sorry, I know this has gotten quite long, but we have the integral from 0 to 2 pi. And one thing I'm a little bit, because I didn't really plan this example out very well, is I'm worried that this might give us 0, which is of course incorrect. But I think it will work. We'll see. But yeah, we have the integral of sine theta over 2, and I even put the absolute values. If you missed that, the absolute value you can find in the math menu under num, if you're trying to ever integrate an absolute value function. But what we end up getting is 4 from that, and cool. So what we have is, it did work. My point is, if you forgot the absolute value there, I think that's when it would give you a value of 0, which my instincts tell me. So let's just see what that, oh no, and I guess it didn't matter. So anyways, not a big deal. But you could have done a simple u sub to solve that integral. But of course, what we end up with is 2a times 4, or 8a, as the length of the cycloid. And again, what we were doing is we were calculating the arc length by starting with the formula for the arc length of a parametric curve. And what we've concluded is the length that traveled was 8 times the a, which was the radius of the circle. For some reason, they were using a instead of r for this radius. So why is this important? And again, essentially, mathematicians had known for quite some time that the length that going back to what this means, remember, it's like as a circle is rolling along, it traces the point along the circle as it rolls. So essentially, it's like if we're imagining an ant on a circle, it would move in such a pattern as that circle is continuing. And so it's kind of interesting to think about the rotation of a tire as it makes one full rotation. How far does that actually travel? And there's a lot of important reasons that this is a useful thing to know. But at the end of the day, that particular curve is just 8 times the radius. It doesn't involve pi at all, which is kind of interesting. And as I was saying earlier, it was a good confirmation for mathematicians to know, okay, that, you know, when I'm doing things with calculus, when I'm integrating using arc length formulas and so forth to do precise demonstrations of these things, it's giving us answers that we know we've proven geometrically many times before using many different techniques. And it's a little bit more simple and elegant of a solution. Well, it's elegant in the form that we can use all of our mathematical curves, our ideas of calculus to do it, as opposed to geometric proof, which, again, there's no problem with geometric proof, but there's sort of a nice neatness to it all at the end of the day.